Hello and welcome back. Today we're going to look at generalized correlations for liquids. Just a quick recap. So far we looked at using virial equation of state and cubic equations of state for calculation of the residual properties. We've also looked at use of thermodynamic tables to calculate the molar volume, residual enthalpy, and residual entropy. Most of our focus so far has been on the vapor phase, although we talked about vapor liquid region beneath the dome in case of cubic equations of state. But most of our focus has been on the vapor phase. What we'll do today is try to look at some of the correlations that are available for calculation of the liquid molar volume and enthalpy changes due to vaporization. So let's start our discussion with some of the correlations for liquid molar volumes. The Racket equation is one of the more popular equations to estimate the molar volume of a saturated liquid. As you can see in this expression, we can calculate the molar volume of the saturated liquid Vsat if we know the molar volume at the critical point, the compressibility factor at the critical point, and then the reduced temperature at whatever temperature we're interested in calculating the saturated liquid molar volume. So let's quickly run through an example for this calculation. We'd like to estimate the molar volume of liquid N-butane at 300 Kelvin. The critical temperature, critical pressure, and the compressibility factor at the critical point are given to us. To be able to do this calculation, as you can see, we have Zc, the compressibility factor at the critical point, which is given to us. And because I know the temperature and Tc, I can calculate Tr, or the reduced temperature at these conditions, which is essentially T over Tc. So that will be 300 over 425.1, which will give me a Tr of 0.7057. So two of the variables on the right hand side I have now, Zc, the compressibility factor at the critical point, and the reduced temperature Tr. What I don't have is Vc. Some of the tables list this volume at the critical point, some tables do not. If they don't, as in this case, we can actually calculate it using the compressibility factor, right? We know that PV is ZRT. This is true even at critical points, so it will be PCVC will be ZCRTC, or if I'm interested in VC, it's essentially ZRT over P at the critical point. I have a value for Z, 83.14. This is in bar cc per mole Kelvin, and the temperature is 425.1 Kelvin over Pc is the critical pressure 37.96 bar. So if I do this calculation, I end up with a value for Vc. In this case, this value of Vc turns out to be 255.1 centimeter cube per mole. What I'm interested in is then Vsat, or the saturated liquid volume at 300 Kelvin, whatever pressure that saturation occurs at, right? And if I want that, then all I need to do is plug in the numbers I just have readily available to me now, times 0.274 to the power 1 minus 0.7057 to the power 2 over 7. And if I simplify this, the number I will get is 102.4 centimeter cube per mole. Turns out this is a fairly good estimate. The actual experimental value at these conditions is, or the measured experimental value at these conditions is 101.85 cc per mole. So that's a decent calculation. Remember, we have no experimental data, we have just estimated this value. So that's a pretty good estimate. Racket equation works in some scenarios, it doesn't. For example, in case of water, I think it's off by about 30% or so at its boiling point, etc. So it depends. In certain cases it works well, in certain cases it may not work well, but it gives us a ballpark figure without any prior experimental data. What we have looked at in case of racket equation is estimation of the molar volume at saturated conditions. But let's say I want to estimate the molar volume for N-butane again, but not at saturated condition, but in a subcooled state. In this case, as you can see, I want to estimate its molar volume at 382.6 Kelvin and 189.8 bar, very subcooled liquid. And what I have as additional information is at 300 Kelvin, the vapor pressure is 2.576 bar, right? So in cases like these, what we do is use what is known as Linderson-Greencorn-Haugen equation, or Haugen correlation in this case. In this scenario, we are given a correlation for the reduced density, which is essentially density over the critical density, or in terms of volume it is Vc over V. This is given as a function of TR and PR. So if we think about it, it's a two-parameter theorem of corresponding states, right? We have two parameters TR and PR which determine what the reduced density is. So we can use this equation straight away, right? For example, if in this scenario, what I can do is I can actually calculate what TR and PR will be in this case. TR would be 382.6 over 425.1, which would be 0.9, and PR will be 189.8 over PC. Again, PC in this case was 37.96. So this will be 5. Remember, these values of TC and PC are same as in the previous problem. So these are the values of TR and PR. What I will do is take these values of TR and PR and locate the corresponding point on the correlation chart. This is 5 and this is 0.9. So I'm there on the chart, and I can go back and see at this point what the value for reduced density is. It's about halfway in between 2 and 2.5. So let's say it is 2.25. So the reduced density I have obtained at these conditions is 2.25. So if I'm interested in calculating the molar volume, then V is going to be Vc over the reduced density. Look at this equation here, right? It is rho over rho C, or Vc over V. So the molar volume itself will be Vc over rho R. And remember, we calculated Vc for N-butane in the previous problem given Zc. So it's 255.1 over 2.25, and that number there turns out to be 112.8 centimeter cube per mole. So not just at saturation condition, there are correlations that are available to estimate the molar volume of the liquid even in a subcooled state. One of the correlation, as we have just used, is an example. Now, these two correlations are widely used for estimating the molar volume of the liquid in saturated state and in the subcooled state. The other thing we're interested in is calculation of enthalpy change upon vaporization, right? If there is a phase change from liquid to vapor or vice versa, what would be the enthalpy change? One of the easy estimate of enthalpy change upon vaporization is obtained using what's known as Troughton's rule. It says that the enthalpy change for vaporization at its normal boiling point is given by this expression right here for most liquids. So if I were to calculate the enthalpy change for N-butane, and I know that its normal boiling point is 273.35 Kelvin, normal boiling point being the boiling point at atmospheric pressure, so P is 1.01325 bars. right? At this pressure, if the boiling point is 272.35 Kelvin, I'm interested in calculating its enthalpy change. All I need to do is simply use Troughton's rule, 10 times RTN. So 10 times R is 8.314 joule per mole Kelvin times Tn is 272.35 Kelvin, which is 22.643 joules per mole. I'm sorry, kilojoules per mole. Notice that I've converted joules to kilojoules, which turns out to be actually a fairly good estimate. Turns out the experimental value for N-butane is about 22.434 kilojoules per mole. So fairly good estimate in this scenario. However, if you take another example, as in this case for water, what we get using Troughton's rule is a delta Hn of 30.99 kilojoules per mole. For water, the normal boiling point is this. We do a similar exercise as earlier, and we end up with a value of 30.99 kilojoules per mole, whereas the actual experimental value is 40.67 kilojoules per mole. So in this case, Troughton's rule doesn't perform as well as in the earlier case. It's about 30% off. But then gives a ballpark figure. It's a quick estimate of enthalpy of vaporization. We can improve the accuracy by using other correlations. One of the more popular correlations used for estimating enthalpy of vaporization at normal boiling point is what is known as Riddle equation, right, which is given by this expression here. The only thing I want to stress is that in this case, the critical pressure PC needs to be in bars for this equation, written as such to be applicable. Let's quickly run through this calculation for estimating enthalpy change for water at its normal boiling point. Right, in this case, we'll try to use it for water again. If I were to use this equation, the first thing I would need is PC, and the critical pressure for water is 220.55 bar. And because I have to calculate TR at the normal boiling point, I would also need TC. And for water, the critical temperature is 647.1 Kelvin. So TRN is going to be Tn over Tc, the reduced, or 372.79 over 647.1, which turns out to be 0.576. Once I have TRN, I can actually plug it everything else in that Riddle equation to get delta Hn. It's going to be RTN, R is 8.314, times Tn is 372.79 times 1.092, logarithm of PC. PC needs to be in bar. We have it in bar. It's 220.55 bar minus 1.013 over 0.93 minus TRN, which is 0.576. If I run through the calculation, I would end up with a value of, again, I'm converting joules into kilojoules. It would be 41.92 kilojoules per mole. Now this turns out to be a better estimate for water. The experimental value again is 40.67 kilojoules per mole, much closer to the experimental value. Remember, this is completely predictive in nature. There is no experimental data that goes into this calculation, so that's a decent estimate. The previous calculation was for enthalpy change upon vaporization at its normal boiling point, either using Troughton's rule or using Riddle equation. Now let's look at calculating enthalpy change upon vaporization at different conditions, not at its normal boiling point, but at other temperatures. So let's take this example. And to be able to do that, of course, we're going to use the equation I have shown here, which is known as Watson's equation. It relates the enthalpy of vaporizations at two different temperatures to the reduced conditions. So to be able to do this calculation, we need enthalpy change of vaporization at one temperature. Then we can calculate it at the other temperature. So let's take this example. We're interested in calculating the enthalpy change of vaporization for water at 500 Kelvin. At 300 Kelvin, the value is known. It's 43.9 kilojoules per mole. So to be able to do this, again, what we need to calculate is the reduced temperature at the two conditions. So I need the critical temperature, which is 647.1 Kelvin for water, and a TR1 turns out to be T1 over TC, so that's 300 over 647.1, which turns out to be 0.4636. Similarly, TR2 is going to be 500 over 647.1, which turns out to be 0.7727. So once I have TR1 and TR2, I can actually calculate delta H2 directly. It will be delta H1, which is 43.9 kilojoules per mole, times 1 minus TR2, which is 0.7727, over 1 minus TR1, which is 0.4636, to the power 0.38 according to the Watson's rule. And this value here turns out to be 31.68 kilojoules per mole. And again, this is a good estimate. The experimental value turns out to be 32.9 kilojoules per mole. So then let's summarize what we have done so far in today's lecture. We looked at calculation of the liquid molar volume at saturated condition and at other conditions using the correlations. We also looked at enthalpy change due to vaporization at its normal boiling point, as well as enthalpy change due to vaporization at other temperatures other than at the normal boiling point, right? So why are we interested in this? It turns out if we have a process where there is a phase change from liquid to vapor or vice versa, these type of calculations come in handy to be able to do enthalpy change, enthalpy calculations for enthalpy change upon vaporization or entropy change upon vaporization, etc. Before we do that, let me quickly talk about entropy change upon vaporization. If we take this example here, delta H2 is 31.68 kilojoules per mole. And if I ask you what would be the entropy change upon vaporization at 500 Kelvin, delta S2, turns out vaporization occurs at a constant temperature, so delta S2 has to be equal to delta H2 over T. We'll come back to this calculation later when we talk about phase equilibrium, but for now let's just say that delta S2 is delta H2 over T, and because I already have delta H2 for phase changes, I can simply divide it with the temperature at which this change occurs, so it would be 31.68 over 500. This would be in joules per mole Kelvin. So not just enthalpy change, I can also calculate the entropy change upon vaporization. Let's run through a problem and see how we can put all of this together, whatever we have talked about so far together. We are interested in calculating enthalpy change for N-butane at 300 Kelvin and 7.53 bar if it changes to a final state of 403.85 Kelvin and 22.776 bar. Bunch of other information is given to us to be able to help us in the calculations. Let's see what it means. So I have A, right, and I have a final state. Let's call this as F. That's the final state. This is my initial state. At the initial state, what is the condition of my species? The temperature is 300 Kelvin and the pressure is 7.53 bar, but I'm given the vapor pressure at 300 Kelvin, vapor pressure is 2.58 bar. So the pressure is more than the vapor pressure, which means the system is going to be in a subcooled liquid state. So this would be a liquid. Let's use a different color for this. This is a liquid, right? And this liquid is at 300 Kelvin and 7.53 bar. Similarly, at its final state F, right? Let's look at what the final state F is. It is at 403.85 Kelvin, and at 400 Kelvin already the vapor pressure is 26.73 bar. At 403 Kelvin, it's going to be more than 26.73 bar. It's going to be slightly higher, right? But definitely more than 22.776 bar. So the final condition, I have not even reached the vapor pressure, which means it's going to be in a superheated state. So lower, the total pressure of the system is lower than the vapor pressure, so I'm in a superheated vapor phase. The temperature is 403.85 Kelvin and the pressure is 22.776 bar. That's where I am. So I'm going from a subcooled liquid state to a superheated vapor state, and I'm interested in calculating the enthalpy change for this process. We can follow a similar logic if one is asked to calculate an entropy change, but let's look at enthalpy change for this particular problem. What we'll do is, because enthalpy is a state property, instead of directly going from state A to state F, we're going to go through a series of steps such that I will choose these steps such that I can readily calculate the enthalpy change for each step very easily. If I were to go from A to F directly, it's going to be very difficult for me to calculate the enthalpy change. So what I would do is break this process down into a series of steps. I would choose these steps such that at each step I can easily calculate the enthalpy change for that particular step, right? So here is a way to do it. One of the ways to do it, I should say. I would transform, or I would change the state of this liquid at 300 Kelvin and 7.53 bar to its boiling temperature. Remember, the boiling temperature is given to us, it is 340.08 Kelvin. So what I'll do is I'll make it into a liquid, all right, but the temperature is going to be 340.08 Kelvin and I will keep the pressure as it is, 7.53 bar. So this is liquid to liquid, temperature has changed, the pressure did not change, okay. Then I'll take this B and vaporize it and make it into a vapor at the same conditions. Vapor at 340.08 Kelvin and 7.53 bar. Let's call this as state C. From state C, this is vapor, this is a real vapor or a non-ideal vapor. It is not going to behave as an ideal gas. So what I'll do is I'll take this vapor and move it to an ideal gas state. So let's call that state as D, and I'm going to give it ideal gas state at 340.08 Kelvin and 7.53 bar. The same conditions, but now in an ideal gas state. Once I'm in an ideal gas state, I'm going to change the temperature and take it to its final temperature. Still in the ideal gas state, but the temperature is its final temperature. Ideal gas, 403.85 Kelvin and 22.776 bar. I've actually taken to the final temperature as well as the final pressure. And finally, from this case, I will take it to a real gas state or superheated vapor for that particular species F. So these are the series of steps I will use to go from state A to state F. Let's draw that actual process is going to be along this red dotted line, and I'm interested in delta H. Let's call that as AF for that particular process. I cannot calculate it directly, so what I'll do is calculate delta HAB, delta HBC, delta HCD, delta HDE, and finally delta HEF. So delta HAF is going to be, right, sum of these delta HAF is delta HA to B plus B to C plus C to D plus D to E plus E to F. Right? So this is what we're going to do. Now, let's see how we can find delta H for each of these steps we have just decided to use. Delta HA to B. Now, if you look at the process, delta HA to B is at the same pressure, we're only changing the temperature, and this is for a liquid. I have Cp for the liquid given to me, right? Cp for the liquid is given 0.1297 kilojoules per mole. So if I were to calculate delta HAB, it's simply TA to TB Cp liquid dt. In this case, Cp liquid is constant. It's not a function of temperature, so I can take it out of the integral. This will turn out to be Tb minus Ta. So that's 0.1297 times 340.08 minus 300, which is 5.198 kilojoules per mole. That's delta HAB. If Cp liquid is not independent of temperature, I can still do the same integration. It's going to be a little bit more elaborate expression, and then I will end up with the numerical result anyway. For delta HBC, right, let's see what it means. This is the enthalpy change due to vaporization at 340 Kelvin, right, going from liquid to vapor. This is not at the normal boiling point. The normal boiling point will be obviously much lower because the boiling point at 7.53 bar is 340, at 1 bar is going to be much lower. So we're not at normal boiling point, but we're at a different condition, right? So we're interested in estimating the delta H vaporization at this condition. And we're of course given the normal boiling point itself, which is 272.6 Kelvin, and delta H vaporization at this condition is 22.42 kilojoules per mole. So what we will do is then use the Watson equation we looked at earlier. Use condition 1 as the normal boiling point and calculate it for condition 2, which is the condition of our interest, right? Let's do that. So delta HBC, let's write that down. Delta HBC is the enthalpy change for vaporization at 340.08 Kelvin. What we know is that the normal boiling point is 272.66 Kelvin, and delta H at the normal boiling point is given to us. It is 22.42 kilojoules per mole, right? So what we'll do is we'll use Watson's rule to calculate, and for using Watson's rule we need TR1 and TR2. TRN is Tn, which is 272.66, over Tc, which is 425.1 Kelvin. Let's write that down. Tn over Tc, so that's 272.66 over 425.1. So that is 0.6414. And TR2 is going to be 340.08 over 425.1, which turns out to be 0.8. So this is TR2. So we can use Watson's equation or Watson's correlation to calculate delta H2. It's going to be delta Hn, which is 22.42, times 1 minus 0.8, 1 minus TR2 by 1 minus TR1, 6414 to the power 0.38. And this value right here turns out to be 17.957 kilojoules per mole. So let's keep that in mind. This is the first value. That's the second value, right? This is delta HBC. So enthalpy of vaporization we have calculated using the Watson's rule. Then the third one, going from vapor at 340.08 Kelvin, right, and 7.53 bar to an ideal gas state at the same condition. What would that be? What would that difference be? Delta HCD. If you think about it, right, if you think about it, delta HCD is H vapor at 340.08, or rather it's actually H for the ideal gas, right? HD minus HC, so that is H for the ideal gas at 340.08 Kelvin and 7.53 bar minus H for the vapor at the same conditions, that is HC, 340.08 Kelvin and 7.53 bar. If you take the difference, if you remember the way we have defined the residual properties, it is the value for the gas minus the ideal gas value. This is opposite of that ideal gas minus that of the enthalpy for the gas. So this is going to be negative of the residual value, HR, negative of the residual enthalpy at the conditions we are looking at. In this case, 340.08 Kelvin and 7.53 bar. How do we calculate the residual enthalpy? One of the ways to do it is use Lee-Kessler tables, let's say, right? We could use Lee-Kessler tables and calculate the residual enthalpy at these conditions, right? So let me quickly run through what TR and PR values are going to be. At this condition, 340.08, TR, remember we said is 0.8, PR is going to be P over PC, so that's going to be 7.53 over PC. Over PC is 37.96 bar for N-butane, which turns out to be 0.1984. So what I'm after then using Lee-Kessler tables is, or you can use any suitable correlations for calculating this residual enthalpy, but what I'm interested in is residual enthalpy for N-butane at PR of 0.1984, TR of 0.8, and for N-butane it turns out the eccentric factor is 0.2. I'm using Lee-Kessler tables. From Lee-Kessler tables, what I get is HR by RTC is HR naught by RTC, right, plus omega times HR 1 by RTC. At the given TR and PR, I'm going to look at the tables and find the values of HR naught and HR 1. If need be, I can interpolate and get these numbers. The final value I have from the tables after interpolation is negative 0.3422 for HR naught by RTC plus omega times HR 1 by RTC is negative 0.5374 at the given TR and PR. I can simplify this and calculate HR, right? And the value I have for HR is 1.589 kilojoules per mole. So I go back, HC to D is negative of HR, right? So it's going to be negative of HR, or this will be 1.589 kilojoules per mole. That is HC to D. This is the residual enthalpy or negative of residual enthalpy at the desired conditions. I have HC to D, then I need to calculate HD to E. And if you look at it, HD to E is essentially the change in an ideal gas state. The pressure is changing as well as the temperature is changing, but if you recall, for an ideal gas, the enthalpy change is independent of pressure, it depends only on temperature. So I can write this equation fairly easily. The enthalpy change for HD to E is going to be a function of temperature alone, TD to TE, CP IG dt. Remember, this is an ideal gas state, so even if the pressure changes, it will not affect enthalpy. The temperature change will affect, and it will be integral of Cp Ig dt. And what we are given is the value of Cp Ig for N-butane. Usually it's a function of temperature. In this case, we're given that it is a constant independent of temperature, so the calculation will be a little easier, right? 0.00.09916 times 403.85 minus 340.08. And this value here turns out to be 3.83 kilojoules per mole. So I have also calculated HD2E. It's an integral of Cpig dt. And the final thing I'm interested in is He to F. Let's look at what this number is. He to F, again, the temperature and pressure are not changing. What is changing is the state of the substance. It goes from an ideal gas state to a superheated vapor, right? So this is exactly the residual property at this condition. If you recall the definition for residual property, He to F is HF minus He. So this is H for the vapor at 403.85 Kelvin and 22.776 bar minus H for the ideal gas at exactly the same condition. This difference, we call it as residual property, as you know by now. So this is HR, the residual property at 403.85 Kelvin and 22.776 bar. So this is exactly the residual property at these conditions, 403.85 Kelvin and 22.776 bar. We're going to use Lee-Kessler tables as we did earlier to calculate this residual property. To be able to do that, we're interested in calculating the reduced temperature. In this case, it turns out to be 0.95, and the reduced pressure, in this case, turns out to be 0.6. So at these reduced temperature and reduced pressure of 0.95 and 0.6 respectively, we're going to go back to the Lee-Kessler tables and look at the values for HR naught by RTC and HR1 by RTC. So I did just that, and it turns out that HR by RTC then will be HR naught by RTC plus omega times HR1 by RTC. Remember, TR is 0.95, PR is 0.6. I go to Lee-Kessler tables and look for these residual values of enthalpy at these temperature, reduced temperature and reduced pressure. And what I have is negative 0.885 for HR naught. Omega, if you remember, is 0.2 for N-butane, and HR1 is 0.994, right? And what this gives me is a value of HR if I multiply it with RTC, and that value turns out to be 3.83 kilojoules per mole. So I have a value of HR, and we said HEF is exactly same as HR at these conditions, so it's going to be 3.83 kilojoules per mole. So we've calculated everything we need in this particular case. So let's write some numbers here. Delta HAB, we calculated it to be 5.198. All these numbers are in kilojoules per mole. Delta HB to C is 17.957. Delta HC to D is 1.589. D to E is 6.323. E to F is 3.83. Now, if you look at these numbers, let me circle them. As you can see, and the total we said, delta H is 34.898. Out of this 34.898, more than half of it is coming from delta HB to C, which is essentially the enthalpy change due to vaporization. That's the major contributor. The residual properties, both of them put together, add to about 5.3, which is less than 10 to 15%. The other big contribution comes from the change in temperature of the gas. Even in the ideal gas state, it's about 6.3 kilojoules per mole. So This sort of gives a summary of the percentage contributions of each of these steps to the total change in the entropy. Like I said again, majority of it of course comes from, more than 50% of it of course comes from the enthalpy change due to vaporization. So this is how we can combine everything we learned today on generalized correlations for liquids. We can use it for calculating enthalpy changes due to vaporization, or calculating the enthalpy changes for processes that involve phase change, as in going from a liquid at one condition, a subcooled liquid, to a superheated vapor, as we demonstrated in this particular example. And like I said earlier, once we calculate enthalpy change, it should be fairly straightforward calculation even for entropy change. We follow a similar path. For each of the small steps, we can calculate the entropy change, and for the step that involves the phase change from liquid to vapor, like I said earlier, we just divide delta H by T. That will give us delta S for the vaporization part. And we add all of them up, we can come up with an entropy change for the total process. So with that, we end today's lecture. What we have done so far then in the lecture is try to use various methods to calculate changes in thermodynamic properties, such as enthalpy, entropy, Gibbs free energy, etc. And in the process, we have used cubic equation of state, we have used virial equation of state, we have used generalized correlations for liquids, etc. to achieve this particular objective. When we come back in the next lecture, we'll start looking at more closely at two-phase systems, which are actually of interest for a lot of chemical engineering separation processes. Thank you.